Let's look at an example that deals with statics fluid pressure. So for this particular example, and let me put a title in here. So this is fluid pressure, and it's static, right? It's not moving. And this is, we're going to look at an example. In this particular example, we're going to have a gate that is underwater. So let's say that we have this wall over here. We have some type of a hinge right there. And then under that hinge, we're going to have a little gate, something like this, let's say. And we're going to have water in this side. Let's say that that's my water level. And what we're going to see is that for this gate not to open, we're going to have a small block on the left hand side, right? So that basically is going to allow water to go from the left hand side of that wall to the right hand side, but not from the right to the left, right? So in this case, we're looking at a cross section of that wall with that gate. Assuming that you're right, this is the gate, and then on top is the wall. And we're going to make the assumption that that gate in particular is going to be 1.5 meters wide. So the gate, 1.5 meters wide. That is 1.5 meters perpendicular to the screen. The dimensions here, we're going to make the assumption that this is 2 meters. And the gate is 1 meter tall. And of course, we have water in that on the right hand side. So what we need to do is we need to find the reaction, the support reactions on that gate. That's our objective. So here we're going to say, I'm going to find the reaction forces on the gate. That's going to be the key problem right here. Okay, so the first thing I'm going to do is I'm going to take this diagram and I'm going to create a diagram that shows a distributed force of the created by the water. So I'm going to make this here on the right hand side just so we can look at both of them together. And what we're going to see is exactly the same drawing, or as close as possible. Here I have the wall, we have our gate. And I want to look at the water pressure. So the water is going to be somewhere over here. All right, so the water pressure is going to be 0 at the level of water, right? Because there is no depth right there. So I'm going to say, well, we can create kind of a triangle like this. And it's a dashed line for a reason, because in reality, all the pressure on top of the gate is not being applied to the gate. So, but that's going to help me draw this diagram, right? This is the actual pressure that is being applied to that gate, something like that. Also, remember that this is a gate that is a three-dimensional gate, so there is a distance that is perpendicular to your screen right now. All right, if we want to calculate the pressure in these 2 points, let's call this point A, and let's call this point over here B. So at those two depths, we have the depth of each point, right? A is at 2 meters, and B is going to be at 3 meters. So we should be able to calculate the pressure. All right, let's go ahead and do that. So let's call this my PA. I'm going to call it PA. Is going to be equal to my density, so it's going to be 1,000 kilograms per cubic meter. Let me write that equation first. So my pressure is going to be rho times G times H. Remember, rho is the density of the fluid, G is your gravitational constant, and then H is going to be the height or the depth that at that particular point. So in this case, it's going to be 1,000 times 9.81 meters over second square times the height, that's going to be 2 meters. All right, if I do that, that's going to give me 19,620. And not sure about the units. Let's look at the units, right? So this over here is kilograms of a cubic meter. And then we have, this is meters over second square, is an acceleration. And the 2 is meters, right? And what we really want is something in terms of a force. And so we need to remember that a Newton is kilograms times meter over second square. So we're going to say we want something in terms of kilograms times meter second square. That's going to be a Newton. And what do we have left? Okay, so if we do that, we have 1 over meter squared. That makes sense. That means that this is Newton over meter square. Now, what you might be thinking, okay, but what's going on there? We don't see a meter square. Well, yes. Remember that the gate has a has a width of 1.5 meters, and that width is going to be perpendicular to your screen right now. All right. So that's the reason why the units are like that. We can simplify that a little bit and say that that is 19.62 kilonewtons over meter square, right? Now, one of the things that I want to do is, instead of dealing this in terms of newtons over meter square, I want to look at that in the cross section. I want to make this a two-dimensional problem. So I'm going to multiply this pressure times the 1.5, the width of that gate, to be able to deal with that distributed force in a much simpler form. So I'm going to call that WA, just to give it a name. So I say that WA is going to be this 19.62 kilonewtons over meter square. I'm going to multiply that for times the 1.5 meters of the width of the gate. And that should give me, see, I have the number here, 29.43 kilonewtons per meter. So now it's much simpler. We're dealing now with a two-dimensional problem. All right, let me look now at the other point. So let's look at point B, right? That's the point A. We can repeat the same calculations for point B. The only difference is that the depth is now 3 meters, it's not 2 meters. And so what we see is that my PB is going to be 1,000 times 9.81 times 3, and that should give me 29,430 newtons over meter square. We can calculate my WB. That's going to be my 29.43 kilonewtons per meter square times my 1.5 meters of the width of that gate, and that should give me 44.14 kilonewtons per meter. Hopefully I'm doing all that math okay. I did it ahead of time, but hopefully I did it right. Okay, very good. So we have now a diagram that shows that at this particular point we have WA, at this particular point we have WB. Now it is just a matter of solving a problem with a distributed force. The plan is, let's try to make this a equivalent point load, and after with that equivalent point load we do our free body diagram, and after the free body diagram we can do the equations of equilibrium. All right, so let's try to do that. So the first thing I'm going to do is I'm going to try to find that point load, right? Equivalent point load. So I'm going to do another diagram. Over here, let's say that that's our gate. This is a little block that is preventing that gate from moving. And now I'm going to have that distributed load. I'm gonna redraw it in here, and you're gonna see why I'm gonna redraw it in here. So let's say you have something like this, right? 2 and all right. So that's my distributed load. Okay. Now, what I want to do is I want to break this down into different sections, right? I'm going to use yellow to say, okay, we have my first section, section 1, right here. And I'm going to use maybe green to use, let's say, okay, we have, this is section number 2. So this is 2. And let's go back to my yellow, and this is going to be number 1. And what we want to do is want to try to find the equivalent point load that has the same effect on that gate than that distributed load. Okay, how does that work? Well, let's put the rest of the information. We know that this is 1 meter. We also know that my WA is equal to 29.43 kilonewtons per meter, and my WB is going to be equal to 44.14 kilonewtons per meter. Very good. So next, what I'm going to do is do the table that we did for composite sections of finding the centroid. Now, notice that the important part of the centroid is going to be my y value, right? So let me put some axes first of all. Here's my x-axis, and let's say that the wall is going to be our y-axis. So we don't really need to find our x bar, right? We need to find our y bar because that distributed force is pushing towards the left. So to define that line of action, we only need our y bar. Okay, very good. So for the table that we use for the centroid of that shape, we have the section, we have our area, and remember that in this case it's not really an area, we're actually calculating a force. So I expect the values of that to be in kilonewtons. We need my y bar, and that will be in meters. Now we need my AI, that's yi bar, and that will be kilonewtons meter. All right, very good. Number 1. Okay, the area of that rectangle, well, the width is going to be this 29.43. So I'm going to write the numbers. I'm going to write the answer at the bottom. Okay, so this is 29.43. And we need to multiply times the height, and that height is 1 meter. And that should give me, of course, 29.43 kilonewtons. My y bar is going to be half a meter because the centroid for that rectangle is right in the middle of it, right? That middle of it is going to be half a meter in the y direction, so this is going to be 0.5 meters. I'm multiplying 29.43 times 0.5, I get 14.71 kilonewtons meter. All right, number 2. For number 2 is that triangle, and for that triangle we're going to see that the width is going to be this part over here only, right? That's my width. So I need to subtract this 44.14 minus 29.43. So, okay. 44.14 minus 29.43. And my height is going to be also 1 meter. Now, the area of the triangle is the width times the height divided by 2. And when I do those calculations, I got 7.355. That will be in kilonewtons if you do the analysis of the units. All right, the centroid of that triangle is going to be somewhere around that. And if you look back to your tables of centroids, where you're going to find that it's going to be 1/3 of the height. And 1/3 of the height is 1/3 of a meter. That's to be my yi bar. And when I multiply that times 7.355, I get 2.452. All right, I need to add these values, and that gives me, So that would be 29.43 plus 7.355 gives me 36.78. And if I add the last column, that would be 14.71 plus 2.452. That will give me 17.16. All right, finally, my y bar is going to be equal to, let's see, I expect it to be a little bit lower than half a meter, right? A little bit less than half of that height. So let's see, so that should be 17.16 over 36.78. That gives me 0.4665 meters. So that sounds about right. That sounds about right. All right, so we got the magnitude of the force. Remember, the magnitude of the force is going to be this, and we got the location of that force, right? With that centroid. So what we can do next is do our free body diagram. All right, so let's do our free body diagram. This is going to look something like this. In this case, I'm going to do just the gate, right? So we have a free body diagram. We need to make sure that we only have the drawing of our object of interest. So we just have the gate, right? That's our gate. Remember that this is an equivalent system. So we're going to have a force applied to that gate. And the magnitude of that is 36.78 kilonewtons. And the height, right? The height of that is going to be 0.4665 meters. I should have made that gate a little bit bigger, but I think you get the idea, right? The three unknown forces that we have, well, we have something at the hinge. Remember, the top was a hinge. And in that case, we're going to have two forces. We're going to have an AX, we're going to have an AY. And at the bottom, we're going to have only one force that is created by that block that was restricting the opening of that gate. So let's call this BX. So there we go. That's the system that we have. Now we can derive our equations of equilibrium. For those equations of equilibrium, I can do sum of the forces in y equal to 0. The only force in y is AY. So now we have our first reaction force, AY equal to 0, right? We can do some of the moments. Let's see, I'm going to do some of the moments about B. That's probably, you can do A or B. The thing is, I have already the distance of that 36 kilonewton force to B, so I'm going to use B. That will be the 36 kilonewton force creates a positive moment, so it will be 36.78, and the perpendicular distance is that 0.4665 meters. And AX creates a negative moment, so that's going to be 1. I forgot to put that distance. That's going to be 1 meter. And I also forgot to put my X and Y axis. Not a very good free body diagram. Here you go. X axis. And let's put our Y axis somewhere in here. There you go. A bit crowded. All right, so the sum of the moments in B is 1 times AX. From here we can say that our AX is that 36.78 times 0.4665. That gives me 17.16 kilonewtons. All right, that's my next answer. 17.2 kilonewtons to keep our three significant figures. Finally, I can do my sum of the forces in X. And the sum of the forces in X have to be equal to 0 because we're in equilibrium. We have a AX, which is 17.2, that's positive. We have a negative 36.78. We have plus BX. For that, we can find that my BX is 19.62 kilonewtons, or BX is equal to 19.6 kilonewtons to keep my three significant figures. That's it. So just to summarize, so to go back and show what the problem was about, we went and started with a gate that is underwater, right? The first step was to define our pressure in different key points. We found that distributed load that described that pressure. And after that, we were able to find an equivalent point load that has the same external influence on that gate. With that point load, now we can do the analysis that we've done with our free body diagram, our equations of equilibrium, and find the reaction forces for that gate.